All right, go ahead and open your books to page 112, please. 112. Just get your here. That's what I'm doing. All right, page 112, please. Page 112. All right. At the bottom of page 112. At the bottom of page 112, they state this fact. I'm not going to write the whole thing out, but it says, let f be differentiable on an interval I, or from A to B. Now, again, notice it said differentiable. Differentiable means not only is it continuous, no breaks, no gaps, but also no sharp points. The derivative exists everywhere. So essentially smooth. A lot of times we say differentiable, we mean smooth. Okay? None of that weird stuff going on. Okay? Because when we get into chapter 4, then we're going to deal with a lot of those technicalities. Okay? But for right now, we're going to leave off most of the technicalities. So anytime it tells you in the directions that the function's differentiable, that's a good thing. They're just telling you it's nothing weird is going to be happening. Okay? So, the fact that we start with the differentiable function is important. So it says max, I'm going to change that a little bit to global. We haven't talked much about those, and we're going to focus on that a lot here in this section. Global max and min values. That means the highest and the lowest points can occur only when f prime equals 0 or at the endpoints. They said stationary points in there, and then in parentheses said where f prime 0, because remember that's what stationary points are, is where the derivative is 0. Okay? Now this again is only true if we know the function's differentiable and it's on a closed interval. Now this is important too, because most of the time we talk about global max and min, we're talking about on an interval from 3 to 7 or whatever. We usually don't go from negative infinity to infinity, because take x cubed for example. If you don't limit its domain, what's the largest value on x cubed? There isn't one, right? Infinity. And the lowest value, negative infinity. I mean, there is not a global max. Remember, global max min means the absolute maximum highest point and the absolute lowest point. That's global max min. That's different than local max min. Okay? So x cubed wouldn't have a global max min if you didn't restrict it to a certain domain. So we're talking about on an interval. So let's think about that a bit. Here'd be an example where the global max would be where? At the left endpoint. We've had some problems like that, right, with the max value. Remember we had a problem where the f prime graph was always positive, and then the homework asked you where's its minimum value at? Well, if f prime is always positive, then f is always increasing, so its minimum value would be back at the left endpoint, right? That kind of thing. So here'd be a function where the global max would be at the left endpoint, the global min would be at the right endpoint. All right? Here'd be a problem. Here'd be a problem where the global max would be here at the local max, where the derivative is 0, but the global min would be at the right endpoint. Okay, so it's lowest, and so that's like a mixture. One of the extreme values as at where the derivative is 0 and 1's at an endpoint. Okay? You could have this scenario like this. Here the global max and mins are also at the local max and mins. The global max mins are where the derivative is 0. They're at stationary points. Okay? So what does this do? What this does for us is it shows us where to check. If I have a question where I want to know what the max and min values are of the function, and a lot of times they don't use the word global or absolute. If they just say find the max and min values, they're talking about global max and min. If they want to know about local max and min, the word local will always be in there. And another term that sometimes is used is relative max or min. A relative max or min is the same as a local max or min. But if it just says find the max and min value, they mean global. Okay? Well, now we know where to look. Okay? And then all that's left then is to plug those numbers in to the function. See which one gives us the biggest output, which one gives us the littlest output. That's one of the ways we do a max-min problem. Okay? So that's an important fact. All right. Later on in this section, turn to page 115, 114, 115. All right, I think I mentioned this the other day. Hey guys. The other day I think I mentioned the term antiderivative. Okay, an antiderivative just means kind of going in reverse as far as doing the derivative. And when we look at the chart, you know, we've talked about f, and then the derivative of that is f prime, and then the derivative of that is f double prime. Right? We could go to f triple prime, and we could keep going and going. Usually don't go past here. If we go in reverse, that's doing the antiderivative. Right? If you go from f double prime to f prime, we say you're taking the antiderivative. If you go from f prime to f, you're taking the antiderivative. And then what is the antiderivative of f? Capital F. And then we typically don't go above that. You know, usually we start with a function lowercase f, because usually our functions are lowercase. You know, think about all the times you've dealt with functions in algebra class, so you've always labeled them as lowercase, almost always. So if you've been using capital F and little f and kind of interchangeably, make sure you can distinguish between those two when you write. All right? Because it makes a big difference then. All right. Now that also tells us that another name for little f would be f prime, big F prime. Right? Big F prime would be the same thing as little f. Right? Since big F is the antiderivative of little f, then if you do the derivative of big F, that should give you little f. And then this would be big F double prime and so forth. Okay? So just understand that notation. Now, a part of your homework is going to be stuff just like what was on this quiz we just went over. They're going to give you a little f graph, and they're going to ask you questions about big F. Well, if you think about that, that's the same thing the problems on the quiz were, where I gave you an f prime graph and asked you questions about little f. They're going to give you a little f graph and ask you questions about big F. It's that same relationship. One of the reasons on the chart that I left this blank over here, right, because you can kind of fill that in for whatever you need. If you're doing problems like the ones on the homework, you can call this row big F and call this row little f. And this row would be little f prime down here. Okay? So that should be easy. I mean, that should not take any extra discussion or anything like that, just so you know that terminology. All right. Think about the rules then. What if I had f of x equals 4x to the fifth? Then what would f prime of x be?
20x to the fourth.
20x to the fourth. And f double prime of x would be 80x to the third by the power rule. What would big F of x be then? 3/2,
2/3.
2/3, I think.
2/3.
X to the 6th, right? Now, so it's a little more different. It's not quite as straightforward as doing the derivative, and that's something actually that you will come to understand all year long. The derivative rules are pretty straightforward. Not that they don't get difficult. They will have their own difficulty. But we'll have a set of rules for derivatives. If the function looks like this, then you do this. If it looks like this, then you do this. With antiderivatives, it's almost a guess and check kind of thing, where you have to say, okay, what would the function had to have been so when I do the derivative, it's not like we'll have a bunch of antiderivative rules. You might say, well, aren't they the derivative rules in reverse? Well, sort of. It's like, what must that function have been so when I do the derivative rule to it, it gives me this. So you say it's 2/3 x to the 6. What you'll find is when we do antiderivatives, we will check a lot. Okay? And not like you do with derivatives. There's no real check to do here. I mean, yeah, you can your check is just do it again and see if you get the same answer. But here your check is do the derivative. 6 times 2/3 would be 4, and then you would drop the power by 1, and it would be a 5. And so, yeah, it does check. Now, there's two things to consider. First thing I'd like then is a rule. If I have f of x equals x to the n power, then what is your rule for what big F would be then? The antiderivative. How can we write that as a rule? Divide by n plus 1, and it's x to the n plus 1. That's exactly right. The rule is, and if you think about this, it makes sense. The derivative rule is a two-step process. Multiply by the power, right? We bring the n down in front, multiply by n, and then decrease the power by 1. If we were to write the rule, the power rule for derivatives, we'd say multiply by the power, decrease the power by 1. So the antiderivative ought to just go in reverse. Increase the power by 1, and then divide by that power. And that's what we do. So if you think about what we did right here, that would make sense. What we did on this one is we took the 4, just left it there. We raised that up to a 6, divided by 6. And sure enough, 4/6 does reduce to 2/3. So we do kind of have a rule for that. All right? And that kind of makes sense. Now, one other thing. I would have said something different for that one. I would have said 2/3 x to the 6th plus 9. That's what I would have said for that. Am I right?
Sure.
Check it.
It doesn't matter. Plus 9 becomes slow.
Because when you do the derivative of this, you get, okay, so
Make it plus 100.
it could have been plus 100, it could have been minus 8, it could have been. Now, how does that connect with something we've already talked about with graphs? Remember the vertical shift? If I give you an f prime graph and have you draw the f graph, what I was having you do was an antiderivative. We just didn't call it that. And one thing we said is there's a whole bunch of different antiderivative graphs. There's a whole bunch of different f graphs that go with that f prime. So if I start with f and want to do the antiderivative, there's a whole bunch of different antiderivatives. They're just all vertical shifts plus a constant that would give you that same derivative. So on our rule here, we're going to write that, C for some constant. And that will be true anytime from here on out when we do an antiderivative. Anytime you do an antiderivative, you can tack on or should tack on a plus C, because there's a whole infinite number of antiderivatives. So any function only has one derivative, but it would have an infinite number of antiderivatives. Okay, but of course, they're only different by that constant. So they're very similar. Okay? All right. So there'll probably be some homework problems that deal with derivatives and antiderivatives. just doing the power rule, the same thing happens with your fractional powers. Don't forget about that. Since we're dividing now, we got to think, what if it was x to the 1/2? You'd raise the power up 1, which would make it what? X to the 3/2, and you divide by 3/2. What's divided by 3/2? Multiply by 2/3, right? So you'll end up multiplying by the reciprocal. So it'd be 2/3 x to the 3/2 plus c. Okay. So there'll be some of those in the homework as well. All right. But the majority of what we need to be able to work on today is on page 121, and we're going to start by just doing a bunch of these together. And these are going to, some of your homework problems are going to be like these. All right? So let's start with number 24. Now we'll pretty much assume most of the ones here for the homework are no calculator. I will, as we go along, show you, okay, if this was a calculator problem, here's what might be done differently. But one of the things that I'm really going to be emphasizing in our next quiz, which is probably middle of next week sometime, will be a lot about this. About finding max and min and inflection points and increasing and decreasing intervals and showing your work a certain way. All right? Because the way they'll be graded, if a problem's worth 6 points, you get 1 point for showing this step and 1 point for showing this and 1 point here and so forth. That's how the AP test is graded. All right? So the way I write this is what I'm looking for. So when I come around and look at homework each day, that's what I'm looking for. Okay? So a big part of what we're learning here is how to show the work. All right, so we got f of x equals 1 plus 2x cubed minus x to the 4th. And they give us this interval, so they're telling us that this is just what I got in writing earlier with the global max min. They want us to find the max and min value of the function. That means they want the output. Max and min value means the y value. Okay, find the max and min value over this closed interval. So, what was the fact we wrote earlier? We got 2 places we have to look. At the endpoints and where the derivative is 0. Right? Yep. Those are the only places the max and mins can be. All right? Now, I'm going to do something here. Well, I'm not going to start it yet. So, we got our endpoints. So, the only thing we have to do is find when the derivative is 0. So, the first thing would be to do the derivative. Okay? So, we're going to do find f prime of x. And it would be what? 6x squared. Right? Because the derivative of 1 is just 0. It's a constant. Slope of 1 is 0. Bring it, okay, just doing the power rule. And we're going to set that equal to 0. Early in the year, I talked about solving equations, how to solve. We're going to talk about how we can use a calculator to help us solve. But on the no calculator part, we've got to be able to solve. On Wednesday of this week, we're going to be working on solving and practice some of our algebra solving equations. Because it's a big deal. We'd have to do it a lot. All right, so what am I going to do to solve that? Take out a 2x squared maybe. Wouldn't have to take out the 2, but the x squared definitely important. Leaves me with okay, so I get to there. Set each thing equal to 0. It's called the zero product property. When 2 or more things are multiplied together making 0, one of them has to be 0, or both. So either 2x squared is 0, or 3 minus 2x is 0. Now, let's make a comment about showing your work. The algebra that you show, I don't really care about. You show as much as you need to be able to solve the problem. Okay? A lot of you could have just stopped by looking at this and said that x was going to be 0, and here it's going to be positive 3/2. Now, if you're having trouble getting that, then go ahead and show more of your work. Add the 2x over to the other side, divide by 2, you get x equals 3/2. So those are my stationary points. It doesn't hurt to label those. So now if I was grading this problem, you would have 1 point for the proper derivative. Probably in the early stages, I would give 1 point for the proper derivative, 1 point for setting it equal to 0. And then the third point would be for getting these stationary points. So this algebra, I would assume you'd need to do it to get it. If you can just look at that and see that the 0 and 3 halves, then good for you. Okay, but probably not. Probably gonna have to do the algebra. All right. If this was a calculator problem, okay, let's just kind of do this at the same time just to make this point. So if we go over here to our calculators, you would have still needed, well, I would assume you would, the problem would be there, obviously. This line would still need to be on your paper. Even if this is a calculator problem, you would have gotten a point for having the derivative and setting it equal to 0. You just still have those 2 points. Now, some people would say, well, I could have used my calculator here to do the, let's have somebody else present here. Okay, who'd I pick here? David. David Reed.
Dang it!
All right. Now, go ahead and type. Go to the template for the derivative. Oh wait, I didn't make you presenter yet. Go ahead and do that though. Go to your template for derivative. Now I'm certainly hoping we wouldn't have to do this for this problem. Have the calculator do this derivative for us.
Far right middle.
All right, Neil.
That one.
No, that's second derivative.
Ah, thanks, Jacob.
That one's derivative.
That one.
Okay, so put next there. Type in 6x squared minus 4x cubed. Oops, time out. Never mind, don't listen to me. Delete all that. Okay, type 1 plus, type the original function. Now again, very seldom will you have to have the calculator do the derivative. If it's that complex a one, possibly. Okay, but very rarely would we do this. But go ahead and hit enter. There's your derivative. Now we want to set that equal to 0, so go to the algebra menu to solve. And then arrow up and grab that, that one. There you go, hit enter. Hit equals 0. Then you have to do, whoops, inside the parentheses, equals 0, comma x. You have to tell it what you're solving for. And now hit enter. Okay, and there's our 0 and 3 halves. Now, if this was a calculator problem, you could have done all that. But on your paper, you still needed to have the derivative written down, set equal to 0, and then these points written on your paper. So you'd still have the same 3 points. The only thing that wouldn't be there would have been this work. So in a no calculator, you're forced to do the work because you have no other way to solve it. And to be honest, even if it was a calculator one, it might be faster. No commentary on how long it took David to type that in. But think about how easy it was. Probably faster to go through and do this algebra than it would have been to sit there and type it on your calculator. Okay? So, very, very important as we go through the next several days that you understand that even if it's a calculator, even if you're doing this stuff on the calculator, the vast majority of what's going to be on your paper is going to be the same. Okay? Going to be exactly the same. All right. Because now, you might say, but geez, why would I do all that? Go to the graph screen, David, and anybody else can too. Go ahead and go up to your scratch pad and hit clear the scratch pad. Probably the fastest way to do that. Okay? Now, yeah, there you go. Okay, now, type in your f of x, or type in 1 plus 2x cubed. Because I'm sure some of you are thinking, well, geez, if I have my calculator and I want to know the highest and lowest values of f from -1 to 2, why don't I just graph the thing and look at it?
did it wrong.
Some people do that wrong, so I won't ever make them the presenter, but I tend to like to make them presenter over and over until they get it. All right. So there we go. Now, from -1 to 2, let me show you another nice little trick that the calculator, another feature that the calculator has. If you go to the menu and the window menu and choose Zoom Fit, letter A down there, and that was a bad suggestion. Let's go back to the menu. I skipped one important step there. Go to Windows Settings. Set your Xmin to -1 because we're given the domain, right? Set your Xmax to 2. Okay, now hit OK or Enter. Or yeah, go down there and hit Enter. Now go to Zoom Fit. Now go back to Windows Zoom and Zoom Fit. What the calculator does is it takes all the values from -1 to 2, it plugs those in, and it gives you a nice window so you can see it. Okay? Well, now you can look at that, and now you can just start tracing. You can trace at -1. You can see that the max is going to be here. You can trace to the max, right? We can find it very easily in our graph screen. But again, it's kind of like if I'm teaching you how to do multiplication in grade school, I would not let you use your calculator, right? Well, the same thing's true here. We're talking about how to find max and min values using calculus. This is the stuff I got to see. So if you want to spend time doing that to check yourself, that's fine. But most of the time, you're not going to want to use up that time. You know how quizzes go. You only got so much time anyway. So you're probably not going to want to do that because you don't get any points for the answer. You will not get any points for your answer if you don't have this supporting work. Okay? All right. So enough with the calculator here for a second. All right. So we found where the max and mins would be. They're going to be either at the endpoints or at the stationary points. What's left now is to do what I call a list of candidates. Okay? A list of candidates. In other words, the only place the highest and lowest values can be is at the endpoints or at the stationary points. So to find out which ones are the highest and which ones are the lowest, we just need to find their y values. They're the F outputs. So all I'm going to do is plug in -1. I'm going to plug in 2. I'm going to plug in 0. And I'm going to plug in 3/2. I'm going to missing what?
On the F0.
Oh, on the screen. Oh, yeah. Okay. All right. And now it's just, and this is, again, let's assume there's no calculator. So now I'm going to go back up here to F, and I'm going to plug in a -1. Okay, so -1 cubed is -1. That's -2 plus 1 is -1. Fourth power would be +1. What did I say that was? So that'd be -1 minus 1. That'd be -2. Okay, put a 2 into there. Be 1 plus 2 cubed is 8. That'd be 16 minus 2 to the 4th. That's 16. So that'd be a 1. Put in a 0. That'd be a 1. And put in a 3/2. That's not going to be quite as much fun. Or maybe it's more fun, depending on your outlook. 3/2 cubed. Let's see. 3 cubed would be 27. 2 cubed is 8. Minus 3/2 to the 4th power. 3 to the 4th power is 81. 2 to the 4th power is 16. So this would be 1 plus 54/8 minus 81 over 16. Yes, you may have to do this. Let's get a common denominator. That'd be 16/16 plus 108/16 minus 81/16, which is what?
A lot of 16.
108 minus 81, that'd be 27 plus 16, that'd be 45/16. Is that right? I think that's right. 124 minus 81. No, is it 43? It's 43. Yeah. 43 sixteenths. 43 sixteenths, which would be 2 and 11 sixteenths. All right. So those are the values. So the answer then, the answer to the question, find the max and min value, I'll just write minimum next to this one and max next to this one. They just wanted the y values, and if we went back to that graph that we had up there a minute ago, I think you would have found the left endpoint was the lowest point, and then the highest point was that local max, which was this stationary point at 3/2. And so that's the value, that's the max value of the function in that interval. Okay? All right. Let's take a look at another one of those. I'll let you do a little more of the work this time. Remember this problem from this document that I sent you a while back, the box problem. And what we're doing here is we're saying, okay, here's a piece of paper, and I want to cut sections out of all 4 corners so that I can fold it and make an open top box. What size corners should I cut out to make a box that has the maximum volume? That's the question. Okay? What box or what size corners should I cut to make a box that's a maximum volume? Well, if we look on here, graphically, we can kind of see, and this is kind of nice, we can just see what's happening here. But if I slide this, we can see now the volume is being plotted right here. Okay? So if I take out bigger and bigger chunks, I get greater and greater volume until some point right in here, it goes the other way. Of course, that would be the stationary point. This is what I'd be interested in, is right here. Okay? How big of things should I cut out of it? So, let's do that. Let's say we're going to start with an 8 by 10 piece of paper. Okay? And we're going to cut out 4 corners. So let's work this through. So what's my unknown? The volume is what I'm trying to maximize, isn't it? So the volume is length times width times height of a box, correct? And that's my function, V. V is my function. I'm trying to find the maximum output of V, right? Maximum volume. Now, what can I label this unknown? Because this is a piece I'm cutting out, right?
Yeah.
So if I just label this X, and I'm going to cut out squares, so those would both be X, correct? So what would be the length? We'll call the length the bottom or the top of the box once I fold it up. 10 minus 2x. So the length would be 10 minus 2x. The width, 8 minus 2x. And the height would be x. Okay? Now, just because of time, well, we could probably FOIL it out faster than we could do it actually type it in our calculator, to be honest with you. So let's FOIL it. We'd have 8 times 10 would be 80. Outers and inners.
16.
Negative 36x, 20 and 16. Plus 4x squared. Then if I distribute the x through, this would be an x, this would be x squared, and this would be x cubed. Correct? So there is my function that I'm trying to maximize. So now we are at the same place we were a minute ago with problem 24. I had a function f that I was trying to find the max and min of. Now I've got a function that I'm trying to find the max of. Now, in problem 24, we had endpoints. X is my variable. What's the littlest x could be? 0. Of course, we wouldn't have a box in, right? It wouldn't have a volume anyway. So that would clearly not be a maximum volume. What's the biggest x could be?
4.
The biggest x could be is 4. So it's often helpful because if x was bigger than 4, that would use up that whole side of the thing. And if x was 4, I again wouldn't have a volume, would I? Because I wouldn't have anything to fold up there. So x is going to have to be here between 0 and 4. All right? So finding out what those endpoints are. But again, in both of those cases, I don't think I'd have a max, I'd have a min. But we could see that in a second. All right, so what's my next step? Do the derivative and set it equal to 0. So v prime would equal, what's the derivative of 80x? 80 minus 72x,
Plus x squared.
and we want to set that equal to 0. All right? A heck of a time with those lines. All right, now, this is one that would probably factor. We could factor out, looks like about a 4. Actually, turns out it doesn't factor. So if this was a no calculator problem, I would have made it come out to be a function that would have factored. But since it didn't, let's go ahead and go on our calculator, go on the calculator part of your handheld, and just do a solve on this. Now, make sure and hit Control-Enter, because it's going to give it to you as radicals. And we'd rather have decimals in this case. Yeah. Oh. Okay. Let me, I can do that while we're getting this solution here. Yeah, I'll have to do that here in a little bit.
It's like x equals 1.
So what do we get?
X equals 1.47247. Or
So I went 3 decimal places.
x
so-
equals 1.47.
3 decimal places.
47.
472.
2.
Okay? Is that rounded or would it round to 3? It doesn't matter. And there's another one, isn't there?
Yeah, or x equals 4.528.
Okay? All right, now those are my stationary points. Correct? And so, again, you have to always justify that something is truly the max or the min. We have a pretty good idea what's going to happen. It's going to be at this one because this is outside of the endpoints. We already talked about how the endpoints don't actually give a maximum. They give a minimum because there would be no volume if you had that scenario. But you need to say that. Now, if you want to write a paragraph repeating what I just said, that would be fine. But this list of candidates is a nice way to do it because now we just say, okay, well, let's try v of 0. Let's try v of 4. Let's try v of 1.472, and we'll throw out 4.528 because it's not inside of our domain. It's too big. We get a negative volume, actually. Well, it's pretty easy to go back to my volume equation. You put a 0 in. Of course, x is in every one of those, so that would be 0. Now, here's where if it was a calculator problem, again, it'd be easy to plug those numbers in. If it's a no calculator problem, which volume equation should you plug into? I would say the factored one is an easier one to plug into. So if I put a 4 in, we can see right here we're going to get 8 minus 8, which is 0, which is going to wipe out all the rest of that. So the volume comes out to be 0. Okay? So now take, and again, since we want our answer to be, and actually I didn't even say what the question was. Is the question what's the max volume, or is the question how big a piece should we cut out? But let's just make sure we're accurate to 3 decimal places. So plug in 1.472, but not 1.472, the unrounded version of 1.472. So remember, the easier way to do this is to type in, I think I should, but let's do it one more time together. Type in 80x. This is the easiest way to plug something into x into a complicated equation. 80x minus 36x squared plus 4x cubed. Type that all in. Or maybe grab it from above. Maybe you had it up there earlier. I don't know. And then put the vertical bar. Okay, somebody's a presenter here. So just type that in. The vertical bar is right next to the trig menu there. You have to hit control. And then you want x equals. Now you can just arrow up here and grab that. Now you're going to have to delete a bunch of stuff. It might have been just faster to type it. Now hit delete. Now you got to delete a bunch of that. Oh, and you got 2x equals now. We have 2x equals in there. Okay, and now hit enter. And this way your answer will be accurate to the third decimal place. If you just put in 1.472, did anybody try just put in 1.4? Was it right? Did you get? Were you still accurate to 3? Okay, so sometimes you get lucky and sometimes you don't. But you want to be careful about using rounded values in your calculations. So what is it? 52? Okay, so now your answer would just depend on what question was asked. If it said, how big of a square should you cut out of the box to get the max volume, you'd say, well, you want to cut a square that's dimensions are 1.472 by 1.472. Okay? If it says, what's the max volume, it might ask both questions. What's the max volume generated when you cut out those squares? Then it would be this. Okay? But that's what a max-min volume, a max-min question looks like. Endpoints and stationary points are the only places max and mins can be. We check those. It's called a list of candidates, and we move on. All right. Now, back to page 121. We're going to do problem number 20. All right, let's. All right, read problem number 20, please. So on page 121, number 20. All right, now when it talked about don't give your answers in decimal form, that's kind of the book's way of saying this is a no calculator problem. Okay, the vast majority of what you're going to be doing for your homework is no calculator. I'm kind of showing you some of the calculator ones. We'll work into some of those as we go through the week, but I just want to emphasize to you that they look pretty much the same. Okay, what you do is pretty much the same. All right, this time the question is different. It talks about local max and mins. That's a whole different question. Now we're talking about the chart. Okay, when does a function have a local max or min? When the derivative is 0, and when the derivative changes from positive to negative. On these problems, we don't care about what the outputs are. We will not be doing list of candidates. List of candidates is global max min. What we care about, notice the direction, or the questions. Where is it? Now they want the x values. Where is the local max min? So now there are some similarities, right? Where are we going to look for local max mins? When the derivative is 0. Still going to look at stationary points. So that part of the question will be the same. But then we're going to check when f prime changes from positive to negative. Now, question A is, where is the function increasing? Well, that's when f prime is positive. Where's it decreasing? When it's negative. So if I just look for my local max and mins, if I just find when f prime is positive, negative, and when it changes from positive to negative, that will answer all of those questions. And I think I showed you this. It's called a sine graph. And we're going to do that right now. So my first step will be what? Do the derivative, which is negative and set it equal to 0. There's 2 points right there. One for the derivative, one for setting it equal to 0. We're finding stationary points. Since this is a no calculator problem, we go to our algebra now. We're going to factor out a 72t to the 7th. Leaves me negative t plus 1. You could have factored out a negative if you'd rather. It's going to come out the same. So I get t equals 0 or 1. Right? It ended up being a 1. My stationary points are 0 and 1. So there's another point for finding the stationary points. But from this point now, this is where it gets different than the global max min. We don't care what the outputs are. We just care when S prime changes from positive to negative. Now, of course, the reason we found the stationary point is if it's going to change from positive to negative, it's got to go through 0. Right? So here's what we do next. We make an S prime number line. Some call it a sign chart or something, but I typically call it a number line. Now, the reason I put 2 marks there is because I have 2 stationary points. This is not a number line like you made in algebra class where you have to label 0, 1, 2, 3, and negative 1, negative 2. No, that's not what we're doing. The only marks I want to put on my number line are my stationary points. So I'm going to put 0 and I'm going to put 1. I don't want anything else on there. That just confuses things. Okay, I always see people going on here and making their number line and putting numbers on. No, no, no. It's not what we want. If we only have 1 stationary point, we'll only have 1 number on that number line. If we have 4 stationary points, we'll have 4 others. Okay. Now, what I'm really interested in here then is the gaps in between those. I'm interested in values out here, so I'm just going to pick a number out here and write it in there really small. I'm going to pick a number in here like 1/2, and I'm going to pick a number out here. Now, I'm not putting marks on my number line for those, though. Okay? I can't emphasize that enough. What I'm interested in what's happening to S prime in those gaps. I know at 0 and 1 that S prime is 0. That's what I already found. All right. So I'm going to take this negative 1. I'm going to do what with it? Plug it into the S prime equation. Now, see, that's different than before also, right? Before, when we were trying to find the max min values of F, we plugged back our list of candidates, we plugged back in the original function because we wanted to see what the outputs were, which ones were the biggest. Now, I'm trying to just see if S prime is positive or negative. So I'm going to take negative 1, I'm going to plug it back here. Now, you know what? It'd be a lot smarter to plug it into the factored version. If I put a negative 1 in there to the 7th power, that's what? Negative. Something. I don't even care. It's just negative. Put a negative 1 in here for t. Positive 1 plus 1 is 2. That's positive. I got a positive times a negative, which is negative. Okay? Now I'm going to plug a 1/2 into there. Again, I don't care what 1/2 to the 7th is. I just care that it's positive. 1/2 to the 7th is going to be positive. Negative 1/2 plus 1 is positive. I'm going to have a positive times a positive. And then 2 to the 7th is positive. Put a 2 in here, it would be negative 2 plus 1. That's negative. So, what I just found there was that my S prime goes from negative to positive to negative at these values. Well, what does it mean if S prime changes negative to positive? Local min at x equals 0, you can just write it right below there. I just answered part D, I think, right there. Part C was where's the local max? It's got a local max at x equals 1. What else did it want? What was question A? S is increasing when S prime is positive. Positive from 0 to 1. There's question A on 20. And B, where's the graph decreasing? It'd be from negative infinity. Notice they didn't give us an interval to look here either, which is okay. Right? That only really mattered in global max min. So from negative infinity to 0 and from 1 to infinity. Same kind of questions we were answering on the last quiz, that earlier quiz in chapter 1, but we did it all with equations. Now, if I wanted to go onto my calculator and graph S prime, what I would probably see if I graphed S prime is something that did this. Okay? Negative, positive, negative. There's 1, there's 0. If I was to graph S prime, it would probably look something like that. And remember what we did back in chapter 1. If you're, whoops, it's S prime. If you're looking at, sorry people watching on the video. There's what we've been doing. If I was to look, you guys should tell me that. All right, so you're sitting back there going, I wonder how long it'll take him to know. Back in chapter 1, we did it graphically. If S prime goes from negative to positive to negative, we know we got a local min there, we got a local max there, right? This sign graph, this number line, tells us all the same information that we had back in chapter 1 when we had an S prime graph. Okay, it gives us the same information, tells us, and we just did that by finding our stationary points, putting those on the number line, and then picking numbers in the intervals to see whether it was positive or negative, whether it was above the x-axis or below the x-axis. All right. Let's think for a second if this question was that S function was the position of a particle moving about on the x-axis, just moving back and forth on the x-axis, instead of just some function that I gave you. Let's say I told you that this S function was a particle moving back and forth, it was its position. And I ask you, when is the particle moving to its right? Think about that now. What's it mean for something moving? Think about the car in Bismarck, in east and west. What's true about the car when it's moving to the right? Its position is increasing, which means its velocity is. So if I said to you that this is a position function for a particle moving on the x-axis, and I said, when is this particle moving to the right? You would want to say to yourself, well, that's like asking, when is its derivative positive? When is its velocity positive? Now, how do I tell when its velocity is positive? How am I going to tell when it's turning to the right? Well, I better figure out when it's going both to the right and the left, and when does it change going right to left? What has to happen before it can, when it can, okay, I didn't say that very well. If I'm gonna give when it's going to its right, I need to know when it started going to its right and when it stops going to its right. What has to happen for it to stop going to its right? It has to turn around. The velocity has to be 0. The derivative has to be 0. Wouldn't I do all of this to answer that question? Instead of asking local max min kind of question, I could ask it as a velocity position kind of question. You do the same thing. You'd say, oh, when's it going to the right? Well, when it stops going to the right is when its velocity is 0, so I better do the derivative, which is velocity. Set it equal to 0. Okay, this is when the particle stops. This number line tells me what about the particle then? What's the particle doing over here? Going left. Then right. Then left. So the answer to the question, when's the particle moving to the right? From 0 to 1. Right? So you would have done all of the same work to answer that question. Okay? Turn to page 122, please. I want you to look at number 52. Read number 52 real quick, please. This kind of helps us to look ahead as we get like to our midterm exam, final exam, on the AP exam. These are the kind of questions that really, and we'll get a practice, look at a lot of these types, but these are the kind of questions then that get into, do you really understand, how this can all connect with when the derivative is 0 and that kind of stuff. But this doesn't sound anything like the questions we've been doing, right? I mean, this doesn't seem like derivative. It doesn't talk about local maximum or any of that. But think about what's going on here. First of all, you're looking at a cubic function. So what's the general shape of a cubic? And since the lead term is positive, it's got to do that, right? So it's got to be up, and maybe it can have a couple of humps in there, and it's got to do that. What's the k do? That's just going to shift it up and down. So then you start thinking about a graph of x cubed. Well, here there'd be how many intercepts? 1. And what would it have to look like to have 2 intercepts? It would have to, one of the humps would have to just touch. Or if it shifts down, maybe this one just touches and then this one, right? So we could have this one come up like that. Be kind of the same thing. That'd be just one, that'd be 2 intercepts. And then 3 intercepts would be like this, right? So then you start thinking, okay, if we shift this down, 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 at some point we're going to hit a spot when there's 2 of them. Then we're going to go and then there's going to be 3 of them, right? And then we're going to shift it down too far, and then there's going to be 2 again. And then we keep shifting down, and then there'll be 1 again, right? Well, when does that interest, what points on the x cubed graph does something change then? I mean, at what point, as I shift down, shift down, shift down, shift down, where am I looking on that x cubed graph? Those stationary points, right? Those are definitely points of interest for me on this graph. So how would we find the stationary points? Do the derivative. Here we go. So now it looks just like these problems we've been doing. So what's the derivative?
3x squared minus.
Luckily, the k disappears, so it's not going to be a factor in this. And you think about it, when you shift this graph up and down, those local max and min stay in the same places, not vertically, but they stay in the same place horizontally. They're x coordinates. So we set that equal to 0. We factor out a 3x. We get x minus 2. So one of them is at x equals 0, and one of them is at 2. Correct? So now what?
So now you would figure out what k value you would put in to make x equals 0 be 0.
When the output is 0, right? What I care about is when those max and mins touch the x-axis. In other words, when y is 0. So I'm going to put a 0 in for x, and then a 0 in for y, and see what k would be. Well, that's easy. k would equal 0, right? That's when that's when I'd have this scenario, right? This scenario here would be when x is 0, that's when y would be 0. That's when it would touch the origin, okay? So that's one important piece of information. Now I've got to plug my 2 in for x, and I've got to think about this when its output would be 0, right? When I put a 2 in for x and get an output of 0. So I put a 0 in for y, and I have 2 cubed is 8. 2 squared is 4 times 3 is 12. So 0 equals negative 4 plus k. So k equals 4, right? Now, the question was, for what values of k do you have 1 intercept, 2 intercepts, 3 intercepts? So we think about this. Here, this one, right here, when the one over here at 2 is touching, that's the one, that's the first time as I shift this thing down, right, as k gets littler and littler, right, that'd be as k goes, right, the bigger k is, it's going to go up. Littler k is coming down. The first time I have to worry about something is at this one, when k is 4, right? So how would I answer when I would only have 1 intercept? When k is greater than 4, so the first question, when k is greater than 4, I'd only have 1 intercept. And then on this one, when k was 0, that was this one. Now imagine that thing keeps going down, keeps going down. Once I get this max off of the x-axis, then I'll only have 1 again. So when k is greater than 4 or when k is less than 0. So that would answer, you see where we could go with this? So I mean, you got some other reasoning to go on here. And when is there going to be 3? Well, that'd be when k is between 0 and 4. So there's going to be 3 of them when k is between 0 and 4. And when is there going to be 2 of them? When k equals 0 or when k equals 4. That's the 2 times when it'll just touch. Okay? Very interesting question. Doesn't seem to have anything to do with derivative or rate of change, right? I mean, it didn't have anything to do with rate of change. But what it had to do with was local max and mins. It had to do with stationary points. So I found the derivative. So right down to this point, it looked just like those other questions we had. Okay, so that was a lot more difficult question, clearly, than the other ones that we were working on. Okay. Your homework for tomorrow, then, everybody's got the Chapter 2 handout, right? What's that?
I don't have that.
You do not have it. We're going to do the line that says 2.4. We're not doing those review ones that are below it. Don't worry about those. Just the line that says 2.4 homework questions. Okay, 3 through 12 are pretty quick and easy ones. Those are the chart kind of questions. I told you about that. They give you a little F graph and they ask you about big F. Well, that's just an FF prime kind of question, like last chapter. So where is it increasing, where is it decreasing? They give you a picture of a graph to look at. There are a couple in there that you do have to think about a little bit, though. And then you get into 19, 23, 25. Those are like the ones we did here. 19 and 23 are just like 20 that we did in our homework. 25 is just like 24 that we did for homework. And then the last 4 are kind of like this last one, the box problem we did, and those. So they take a little time, take a little thinking, but